start the presentation. Hello, everyone. Good afternoon. My name is Ajay Jacob, and I am the Director of Projects in the California Dreams Hub. Today, we have Professor Joshua Yang from USC, who is giving a talk on real-time RF signal processing in extreme environments with Memristors. Professor Joshua Yang is the Arthur B. Freeman Chair Professor in the Department of Electrical Engineering at the University of Southern California at the USC. His research focused on post-CMOS hardware for neuromorphic computing, machine learning, artificial intelligence, in which he has published several pioneering publications, papers, and holds more than 120 granted US patents. Dr. Yang is a founding chair of the IEEE Neuromorphic Computing Technical Committee. He's a director of the USC Air Force Center of Excellence on Neuromorphic Computing. And he's also a co-founder of TetraMem Incorporated. It's a Memristor company. It's a company based on manufacturing Memristors or Memristor-based products. He has received numerous honors, including the USC Senior Faculty Research Award and the Powell Faculty Research Award. He serves as an associate editor of Science Advances, AAAS, IEEE EDM, and Dr. Yang is a Clarivate highly cited researcher and ranked among the top scientists by research.com. He's a fellow of IEEE and National Academy of Inventors. I welcome Professor Yang to give this presentation. Professor Yang, the stage is yours.
Great, thank you. Thanks for the introduction, and good afternoon, everyone. So I hope today for my presentation, I can provide a solution for real-time RF signal processing in extreme environment. And so I hope through this seminar you can see that this is an ideal topic for another hub project in terms of topic fitness, in terms of the technology readiness, and also in terms of the relevance to DoD. Okay, so I will first give an introduction to talk about the background and also introduce Memristors. And then I'm going to talk about how to perform real-time and efficient temporal signal processing with the Memristor systems. And then I'm going to talk about the robustness of the system and extreme environment. Okay, so let's first see an example of the task we are interested in solving. Right? So for RF signal processing, we know before we demodulate RF signal, we will need to know what kind of modulation method the RF signal is made of. So basically you need to understand, typically there are 11 types of modulation scheme for RF signal. We wanted to know which one is the RF signal you are dealing with, using one of the 11, for example. So obviously we can do that, but the question is, can you do it in real time? Can you do it with low energy? And even can you do it under extreme environment, right? So that turned out to be very, very challenging. So here you can see the current solution is a purely digital solution. So you will have the system here to transform the RF signal from the time domain to spectral domain. And then you wanted to use a digital computer or purely CMOS ASIC to perform some processing task so that you can classify the spectral signal, or you can make some decisions or trigger some following actions. So this whole thing, if you do it in using a purely digital system, it turned out to be really power hungry and with large latency. So the proposed solution is to use Memristor system, which will lead to ultra low power and real-time processing, and actually can be done under extreme environment. So the reason we can do it really fast with low energy is because a Memristor system can greatly accelerate vector matrix multiplication computing with very low energy consumption. So that's Memristor system is good at to accelerate vector matrix multiplications. And if you look at what you needed to do in perform that task, so you need to perform some sort of a signal conversion using FFT or DFT. The major computing there are actually vector matrix multiplications. And then you get a spectral signal. You can use a neural network to recognize the spectra, spectra as a fingerprint. You can classify the spectral signal with a neural network. And you can use a neural network to make a decision, to trigger some action. So the neural network, it turned out the majority of the computing, over 85% of the computing is nothing else but vector matrix multiplications. So that is why if you have a vector matrix multiplication accelerator, you can really solve this problem, with real time and ultra low power. So why cannot we do a similar thing, with the digital system, with fast speed and low energy consumption? What is the problem with the digital system? So our current digital system, the hardware is way behind the demand. So as you can see shown here, this is you talk about neural network. So the x-axis is time. The y-axis is how much computing performance you need in terms of petaflops for how many days to train a certain neural network. So basically, that's the computing performance requirement. And as you can see here, in the last few years, this hardware performance requirement has increased by 1 million times. And around the same time, if you look at how much the real hardware represented by NVIDIA GPUs has been improved, it is about 100 times. So there is a huge gap. And you can see with this trend, you will never be able to meet the requirement just by using the traditional CMOS digital system. You have to use some disruptive technologies such as RAM to do that. RAM is one type of memristors. Okay, so now the question is why our digital system cannot drastically improve anymore. Okay, so the problems are both at the device level and architecture level. So at the device level, we all know Moore's law has come to an end, right? It's truly approached the physical limit now. And also there is something called a memory wall. Basically, the memory performance is below the processor, and the gap is increasing over time, not decreasing. So memory is really a bottleneck. And the third thing is the height wall, because Dennett scaling law has ended over probably 15 years ago, which means even if you can continually make the transistors smaller, so you can cram more devices within the same area, but the power density in that area also increases drastically. You cannot even dissipate the heat. Then you're going to even burn your chip if you run them in full speed. So those are the challenges at the device level. At the architecture level, the problem is as big or even bigger. That's the Neumann bottleneck issue. So our current digital system, including GPUs, and they are made of a Neumann architecture, which means you have a physically separate CPU and memory. They are physically separated so that you store your information in the memory. When you need to process it, you send it to the processor to get it processed. Then you send the result back, store here. Then you take the next piece of data to the CPU to process it. So you do this kind of in sequential if you just have one core. If you have more core, you can do it a little bit, in parallel. That's what a GPU does. But you do not have a huge parallelism with many cores. And but this Neumann architecture was perfectly fine in the past. The reason was in the past, our computing did not involve a lot of data. But nowadays, most of the computing, including RF signal processing, are data-centric. So now constantly shuttling data between these two units become really time-consuming, energy-consuming, and it is a sequential process. It leads to a lot of latency. It is a digital system. Our world is analog. The signal is analog, including RF signal. So you need to first convert the signal into digital, then you process it. But that conversion between analog and digital is notoriously energy and time consuming. So to solve those issues, we have to learn from something, actually, something that can be very efficient in dealing with large data. So believe it or not, the most efficient computing system, especially energy efficient computing system, is the brain. So the brain does the computing using a network. It is a network of neurons connected by synapses. Synapses here are the memory. You store your information in the network. You process your information where it is stored. Basically, it is in-memory computing. You don't need to move your data anymore. So that is a huge deal. Save you a lot of time and energy. In addition, you can process data simultaneously in the network in parallel. This is with the ultimate parallelism, massive parallel processing, okay? And this network can deal with analog data directly, so it is analog computing. Now with these three principles in your system, you already have a very efficient and very fast computing accelerator that can be used to solve our RF signal processing problem and many other problems. And there's more. This neural network, all we know, brain can perform learning much more efficient than our digital system as well. That is because the brain is using neural science principles for learning. That's why it is much more data efficient, much more energy efficient, and also much more time efficient. So that is a different issue. Today, we are going to mainly focus on these three principles that can make our computing in real time with low energy consumption. So in order to implement these principles in our computing system, we will need a new type of devices. Okay, so Memristor is a leading candidate for such tasks. For those who are not familiar with Memristor, this is a simple introduction. The device structure is very simple. You typically have three layers. This is a functioning switching oxide layer, and you have two electrodes. The device is simple. Structure is simple, but it has very rich materials, physics, chemistry, electrical issues that allow us to have rich device property for our applications. The typical device structure is a crossbar form like this. You apply electric field between the two electrodes, you can change the conductance. A simplified conductance change mechanism, the switching mechanism is shown here. Let's see the switching material here is a model material like titanium oxide. Titanium oxide can be viewed as a semiconductor material with wide band gap. As a semiconductor material, it can be doped, for example, by oxygen vacancies. Then the doped region is conducting. So the undoped region have a typical metal semiconductor Schottky barrier. So the beauty here is the dopant are mobile. This is different from the dopant in silicon, which is immobile. So you can use a larger electrical field to move the dopant. So you can move the dopant to the top region, also dope this region. Then the total conductance between the two electrodes is low, conductance is high, so the device is in on state. And you can read out this on state with a small voltage without disturbing it, right? So if you want to change it to a different value, for example, turn it off, you just reverse the voltage polarity, you can move the vacancies back. The dopant back, then you recover your off state, right? So there you can have other type of dopant. I'm not going to talk about that. Basically, that's a switching mechanism. And then with such a switching mechanism, the device turned out to be very capable. For example, you can get a very fast switching. We have shown that we can switch the device on and off repeatedly within 85 picoseconds. That's very fast. So we also show that this is not just a binary memory with on and off state. In fact, you can have many intermediate resistance levels. We have achieved 2048 levels for each device. That is equivalent to 11 bit per cell. The device is highly scalable. In the 2D, you can see here we make the device as small as 2 nanometer by 2 nanometer at each crossing point. That is one memristor, and they can still switch nicely. In addition, the device is stackable. So you can stack them in 3D, which is not only a way to increase the density, but also the way to increase the massive connection. The connectivity number is really the essence of a network. So we have shown we stack them up to 8 layers, and we program this 3D memristor array into kernels to process video information. So that has been experimentally demonstrated. In addition, such a device, the switching, as you have seen, it's relying on electrical movement of ions, which is very similar to what the biosynapse neuron function. They also function based on ion motion. That's why the physical similarity between memristor and the biosynapse neurons makes the memristor very interesting element to emulate, not just simulate the synapse and neurons to build a neural network. That is not what we're going to talk about today either, but just to let you know. And also the device can be used in extreme environment, as you see here, and very high radiation dose. The device does not even change, its resistant state. It is highly tolerant to radiation. The device can also sustain high temperature. This is something we published a while ago, and the more recent data, and we have shown actually a much higher temperature tolerance for the device to function. There are other good properties such as CMOS compatibility, non-volatility, non-destructive reading, low cost, so on and so forth. I'm not going to go into detail for those. Rather, let's just summarize this part. The memoristive devices can have different properties that can be used for different type of computing. And using memoristic devices for computing has been the research focus in my group in the last few years. Some of our major results are summarized here, which can be categorized into 3 groups. In the first group, we're just trying to build a machine learning accelerator, to accelerate vector matrix multiplications. The goal is to get high throughput and energy efficiency. This is the most relevant part for the RF signal processing we're going to talk about today. And in this category, we're trying to use the device to build faithful artificial synapse, artificial neurons, put them together to build a neural network that can lead to advanced intelligence, in addition to the efficiency and high throughput. In the third category, we're trying to combine those devices with sensors, to build an intelligent system, so they can operate with each other in the analog domain, just like we operate RF signal with a computing element in analog domain. So that is also relevant. But due to the time limit, I'm mainly going to talk about how do we use Memristor to efficiently accelerate vector matrix multiplications. So that is used to perform real-time, efficient temporal signal processing, including RF signal. So this slide is talking about the fundamental mechanism. How do we use a Memristor device to efficiently accelerate a vector matrix multiplication? This may sound trivial to solve vector matrix multiplications, but as I said, this actually is the fundamental part for many computing, including RF signal processing, including neural network. It's mainly about vector matrix multiplication, which, however, is something our digital computer is not good at. Part of the reason is due to it involves a lot of data. The Neumann architecture is not good in dealing with it. For example, if we use a digital system to calculate this vector matrix multiplication, what you do is you take an element in the vector and you multiply it with an element of the matrix, and you get a result you store in the memory, and then you take this one to multiply the next piece, and then you get a result you store here. You do this one by one, you finish it, then you do the summation. You can see this is sequential process, and you visit memory a lot. That takes a lot of time and energy. So if you use a Memristor crossbar array to do this, you can, in principle, finish the computing within one cycle. One computing cycle, you can get the vector matrix multiplication result, the dot product. So this is how you do that. And you can map the matrix into the conductance matrix of a Memristor. So basically, you can program each Memristor into a certain conductance value to represent the mathematical element in the matrix you're going to multiply this. So you then you can use analog voltage in the vector to represent the numbers in the vector to be multiplied. So to perform the vector matrix multiplication, you just need to apply those voltages to those rows in parallel simultaneously. Then you just collect the current at the end of the column. The current is really the dot product of the vector multiply this. So the reason is you apply voltage to a resistor. At here, you're going to get a current. The current is really the multiplication result of the voltage and the conductance. That is Ohm's law. Basically, Ohm's law has done the multiplication for us. It does this everywhere simultaneously. If you collect the current here, You're going to add those current results together simultaneously. That's Kirchhoff's current law. Basically, this Kirchhoff's current law has done the summation for us. It does this simultaneously everywhere. So basically, to get the dot product, you just need to apply voltage, collect current, one computing cycle, you get the result. If you think about it, it is in-memory computing. It is parallel computing with the ultimate parallelism. It is analog computing. That's why it can lead to orders of magnitude improvement in speed and energy efficiency. Okay, so to prove this concept, we have made the hardware a while ago. So the CMOS part was made in the foundry, and the Memristor part was made in the lab. And so we show that we can perform the vector matrix multiplication with really high energy efficiency and throughput. So that was great. However, analog computing has its weakness as well. A major challenge is its precision. It's typically low compared to digital. So in order to enhance the precision, you need to do something at the device level and also circuit level. So first, at device level, it turned out that Memristor is not a resistor after all. It is noisier than a resistor typically. If you switch the device freshly to a certain resistance state, you give it a small reading voltage, constant voltage, you read the current, the blue curve is typically what you get. You can see the current fluctuating. This is the random telegraph noise. With such big noise, you cannot have two conductance levels close to each other and still distinguishable. Fortunately, we figured out the mechanism of the RTN, and we developed a very simple electrical operation protocol to denoise it. After denoise, you can see the noise, the reading becomes a red curve, and the noise is very low. So now you can have two conductance levels very close to each other and still distinguishable. So that allows you to have many, many conductance levels, like more than 2048 levels for each of the device in the array. So each cell is capable of 11-bit. Okay, if you think about it, SRAM, it is like 6 transistors to represent 1 bit information. Right? This is the one cell can represent 11-bit information. Okay, so we also, have the materials characterization to show what is the denoise mechanism. I'm not going to go into detail of those. So this actually has been done on the device we made in research foundry as well. So you can see the Memristor is integrated on top of CMOS, so the Memristors. And so this device made on an 8-inch wafer has a very good uniformity across the entire wafer. So this can be seen by this plot. So this plot is like you pick one device from each of the dies. And so you program the device from different dies to the same conductance level, for example, this conductance level. So you can see, even though they are from different dies across the wafer, they can be programmed on to the same conductance level with a very narrow distribution. That shows the uniformity across the entire wafer. And more recently, we even make it in a 12-inch wafer, and each of the die here is a system on chip. This each SoC has 10 NPUs, that's a neuron processing unit, and each NPU has one Memristor crossbar array Each array size is 256 by 256. And we also have on-chip CPU, SRAM. So basically, you can program each SoC to different neural network, for example, to perform computing tasks. So this is a video to show you that we can program the SoC here to process handwritten numbers. So you probably have seen this, with others demonstration previously, but the difference here is everything is done on chip here, and the computer here is just used to visualize the input and output, and everything is done in real time. Okay, the sample is really written by the student using the mouse here. It's not the typical sample, in the data set of MNIST. So you can see the student is writing number, and the chip is process it in real time and tell you what's the number that is going to be, give you the top 3 guess. So of course the top one always with the highest confidence level. So since this is real time, before you even finish writing the number, the chip already start to give you the guess what it is. For example, you can see this initially think it's 5, then now it's 7. No, actually it's 2. No, 8 actually is 8. So everything is done in real time, and everything is done on chip. So this is the neural network applications. For such application, you don't really need a very high precision. 8-bit precision is sufficient, but there are other applications such as signal processing, training, or scientific computing. You will need a higher precision, for which you will have to do something at the circuit level. In a more recent work, we have designed the architecture and algorithm which allow us to obtain arbitrary high precision in principle. So the concept is shown in this slide. I'm not going to go into the detail, but rather to say the key thing here is instead of using just one cell to represent one number, we can use a weighted sum of multiple cells to represent one number. And the weight here for each cell is dynamic, not a fixed weight like what other previous demo was. So this dynamic weight allows to much more efficiently compensate the error in the analog device programming. So as shown here, with just 3 memristors, we can, to represent one number, we can reduce the error from 10% to 0.1% by 1,000 times. So the overhead of the circuit is minimal. This is really feasible. And we have experimentally demonstrated this with the SoC chip. So we demonstrate that we can use it to solve partial differential equation like a Poisson equation with 10 to minus 15 or lower error for solving those partial differential equation. We use it to demonstrate other applications like more complicated situation, like a magneto-hydrodynamic system simulation. You can see this is digital computing, this is analog, and they have a similar result. The difference is the analog one give you a much higher energy efficiency, almost 2 orders of magnitude higher energy efficiency. Okay. So now you have the device and the circuit there can have a high precision. It can do something more than just neural network. For example, we can use it to do signal processing for RF signal. And we can even combine this RF signal processing part with the neural network. So we can form a fused network. We perform these 2 types of computing within one network frame so that they can have a seamless connection even in analog domain. So that concept is shown here. So you can have a fused network, and the first layer could be the DFT layer, which is used to transfer the time domain signal into frequency domain. What you need to do is just program a Memristor array into the DFT coefficient. DFT is discrete Fourier transform. So with this, you just perform a vector matrix multiplication with the crossbar array that can transform the temporal signal into spectral signal within one computing cycle. Then you have spectra of the signal. Spectra can serve as a fingerprint, which can be classified by the following neural network. And then you can, know what the signal is. Then with more neural network, you can even do more, such as decision making or trigger some activities. That can all be done by Memristor-based neural network. And so this is an analog system. You only convert the data into digital once you significantly shrink the size, to information. That will make it, the burden of ADC conversion much less. So to demonstrate this experimentally, next, we're going to first demonstrate our chip can perform DFT computing. Then we're going to demonstrate our chip can perform the convolutional neural network computing. And then we can demonstrate the chip can perform all these together within one chip. Okay. So for the DFT, this is we program the DFT coefficient on the Memristor crossbar array with relatively low error. And then we use this to process audio information, right, which in real time. So it is using this chip programmed with DFT to convert the audio information into spectral domain. This is in the time domain, and this is converted signal by the chip into frequency domain. To compare, we also did this with the software digital system, the green curve. You can see the green red one is from the hardware, analog hardware, compared to the digital system, and they are quite similar in getting the spectra. Okay, so this demonstrates the DFT part. Now we program a convolutional neural network on the chip, so use it to see real-time video processing. So basically to detect the edge of the objects here in real time. As you can see, this shows the neural network, convolutional neural network function can be done on the chip in real time. Okay, so now we have both DFT and neural network. Then we put them together to form the fused network, and we program the entire fused network on this chip, and then use this chip to perform the real-time temporal information processing. Everything is done on this chip, and the student is reading this number. It's audio signal. It will be converted into spectra by DFT. Then the spectra is going to classify by the neural network. Everything is done in real time. So of course, this demonstrates in principle, you can do this for RF as well, except the chip here is not built for that purpose, and the CPU was not powerful enough. The crossbar array is not large enough to do the RF signal directly yet, but this shows the principle. Okay, so now we think we have a feasible approach to perform the a modulation scheme classification in real time and low energy. So we did it in a simulation, and we can see here by using a DFT and a 2-layer of fully connected neural network. In simulation, we can process RF signal to do the modulation classification task with over 90% of accuracy, which is comparable to what you can obtain from software. Okay, so this is simulation. You know, like I said, the chip is not designed for such high speed yet. So that's why in the ongoing project, we are building hardware that handles faster speed. Right? So this, because building a fully integrated chip would be too costly at this moment, we did this at the PCB level. And the input signal, we already taped out IC circuit for the sample and holding, and to basically capture the RF signal, and the RF signal is represented by voltage, analog voltage that will input to the Memristor crossbar array for DFT, then go to another Memristor crossbar array for convolutional neural network and to classify the signal. And then finally you have the signal, you know, almost the final information, very small size, then you convert it into digital. And then you show it in the PC to visualize what you get. So this whole system can, of course, be shrinked on an integrated chip. But like I said, that will cost more time and money. So that would be an ideal hub project because this is really something important for DoD. Okay, so with that, now let me switch gear, talk a little bit about you know, the robustness of the system and the extreme environment. So for the case, you know, you have warfare or battlefield typo here, and in space, you will have to deal with the extreme environment. Okay, so for this, we can actually leverage a center we launched last year. So this is a center of excellence. The center name is a Center of Neuromorphic Computing and Extreme Environment, short for concrete. So this concrete center is a multi-university center led by USC, sponsored by AFOSR, Air Force RX Lab for materials, RLRI Lab for information processing. So together we are studying materials device circuit algorithm to get the neuromorphic computing system and extreme environment. So why we care neuromorphic computing and extreme environment? That is because we are facing a lot of mission critical challenges. In those cases, we need to deal with harsh environment, including radiation, high or low temperatures, thermal instability, electromagnetic interference. And in such case, we also need for high energy efficiency, real-time autonomy beyond Earth or battlefield support. Okay. The reason is you either under bandwidth limit or the communication is denied or not available, or the task is very latency sensitive. And the neuromorphic computing system can offer unique advantages to deal with these issues. The Memristor-based architecture can provide radiation and temperature tolerance, and it can be super fast and self-learning, self-healing, and energy efficient. It has very compact form, and it can be deployed on the edge. So this is ideal for edge intelligence for unmanned vehicles, hypersonic missile aircraft, spacecraft, rovers, and autonomous sensing systems. Why now? Right? We are facing, the era of space and tactical autonomy. Some competing thread, cloud. We need a cloud-free AI, and we are facing multi-agent swarms, operate under extreme limit of size, weight, and performance. In the space project, where the Artemis, Mars, lunar surface missions, those all need intelligence on board locally. Under this, we will need to have environment-driven design because the traditional silicon-based processors fail under extreme radiation temperature. Memristive neuromorphic devices expect inherent robustness and adaptivity. I will show you some of that result, and it is capable of a long duration, autonomous operation without active cooling and shielding. So autonomous is different from automatic. Automatic is you programmed, right? Autonomous is something it can control itself without being, predetermined by programming. So the opportunity of HARP project can unify materials, device, circuit, architecture, and algorithm, and one initiative to deliver a real-time RF SoC for extreme edge applications. And if you compare the benefit of the proposed approach versus the traditional approach, so for radiation and temperature, traditional approach, digital system need shielding, redundancy, and the proposed approach is inherent tolerant to radiation and no refresh needed when you operate at far edge. And latency, if you rely on the cloud, the latency will be high. But for this on-chip intelligence, you can have real-time local decision-making, self-healing, and adaptation. Power-wise, traditional system, you will need a high power from CPU, GPUs. This, you will have ultra-low power analog systems. Size-wise, you will have a bulky system plus cooling. Here, you just have a scalable passive core chiplets. The outcome would be to deliver adaptive, survivable, and efficient computing architectures for RF that no conventional paradigm can match in extreme conditions. So this is just show one piece of data to see that the Memristive SoC can actually tolerate radiation when you use it. This is a chip, programmed into Omnis dataset so that we can, before exposure, we can measure the handwritten digits, classification accuracy to be this number. And after we put this chip and the radiation environment to get a pretty high radiation dose, and then we measure the classification accuracy. You can see it actually didn't drop. And then you leave, this shows the radiation tolerance. Then you leave the chip there at ambient temperature in this case. After 6 months, you measure it again. You can see the classification accuracy didn't drop either. So basically, this shows the retention, right? You put something on the space, you don't want to refresh it frequently, and you may not even be able to do that. This shows the retention of the system. And this has been repeated with different chips and shows similar result. Okay, so to summarize, I hope the takeaway message is real-time RF signal processing with low power and extreme environment remains unreachable for traditional digital system, but Memristor-based fused network consisting of DFT, for example, and neural networks offers a promising solution. Memristor can sustain extreme environment, as we have shown the radiation tolerance, and we have data also show the very high temperature tolerance as well. So finally, I'd like to thank all the sponsors, and I will stop here to see if there's any question.
Thank you, Joshua. Oh, really, really impressive work, So your presentation was really engaging, and these results, which is very product-based research, I felt it was very compelling to showcase the use of memristors in the radiation hardened environment as well. In addition to the previous works that you have done. Great. We have one question from the audience, which is I can read out, or Tausin, you can come and ask the question.
Hello, thank you very much for this very interesting talk. I was just wondering if, for example, in your matrix multiplications, do you have still pure linearity in your multiplication for low and high voltages, or do you have any nonlinear effects?
Right, so that is a very good question. So if you look at the IV curve of our device, so we're talking about inference, right? So what we care is whether the current voltage relation is linear or not. As you can see, they have a pretty good, linearity between current voltage relation, which means each device is represent a fixed number regardless of the reading voltage, regardless of your input vector number, the cell represent a relatively fixed number. That is what you need to get a high accurate dot product. So the device we're using, you can see is quite linear. So does that answer your question?
Perfect. I was just wondering in the low part, because of the colors, there are so many curves that
here, right?
Yeah, in this region also, but I imagine that it is a visual effect, but
exactly, yes. This is really the visual effect. If we zoom in here, it is also quite linear.
Thank you very much. Great work. Thank you.
Thank you.
Any other question from the audience? It seems, yeah, there is.
I have a question about your radiation hard test. So, do you have any idea what's the mechanism of the failure under that radiation condition?
Right. So in our radiation test, we did not see failure at the system performance level, right? Because without radiation, right, you have the MNIST classification accuracy this, and after a pretty huge radiation, and we measure the tip again, and we can see if there's anything, the classification accuracy is actually even better. So that is due to the variance during reading. So we didn't see the degradation of the chip performance, even after high.
Let me ask in the other way. What makes your technology more radiation tolerant than others?
Right. Yeah. Right. So others that we mainly thinking about, the electronic-based system like DRAM, SRAM, flash, right? So those you think about their memory, there is really because of electron. So when you have those radiation, then you create a lot of electron hole pair, and that can directly, make the issues, troubles to those devices. Here, we are relying on ions to represent the memory, the position of the ions. So the chance such radiation going to hit the ion is very small, even though you can also create the electron hole pair, and it's not going to be large enough to affect the ions, unless you do over, really unnecessarily large amount of dose. And we do see to a very, very high, you're never going to see that in space, that can still also change the device behavior. Yeah.
This is only about the ionization, the charging effect. Have you thought about those ions, those radiation masses?
Yeah. Yes, we have been doing other type of radiation. So we also doing it in situ. We so far, what we have seen is this type of technology is much more radiation tolerant. And of course, we haven't finished, all types of testing, and but the initial result seems to be this is much more robust than the traditional digital system.
That sounds great. Thank you.
Yeah. Thank you.
Thank you, Joshua. There is one question from Sri Priya. Sri Priya, you want to ask the question? It's a related question that Joshua asked.
Yes, basically, the question that I had was the TID applied here. Was it a gamma ray dose, or did you try any other kind of exposure? I was wondering what the nature of the dose was.
Right. So we are trying, X-ray and others, and so it's still ongoing and have not been published. And so we will, once we have a conclusion, systematic study, we will publish those later. Actually, we did this with Arizona State University. The expert there, Hugh and Matt. So yeah, and they have done systematic measurement on other type of memory and CMOS as well. So you can check some of their excellent papers to learn more. Yeah.
Okay, thank you so much.
Yeah, thanks.
Thank you, Joshua. I have one follow-up question from what Thurston was asked. I mean, I just asked in a very different way. You showed that the response that you're getting is linear, but assume you have variability or you have the non-ideality, because Memristor devices are considered to be non-ideal. They provide non-ideality, but you're showing the linearity. But let's assume it is non-ideality. There is non-ideality there. And how do you address, let's say, the cycle-to-cycle variation, or the drift, or if there is a limited precision? How will you address that in your analog SoC? Especially when you're trying to do these type of DFT or neural inference. I mean, in extreme environment, this is probably very important to address. I mean, you're showing a very different picture here, but I'm talking in terms of when you have the non-idealities.
Right. So there are different type of nonlinearities. So for example, if this IV is not linear and you wanted to have for example other operation regions which has even higher resistance, have other benefit, you can have a nonlinear IV curve, right? So in that case, you will need to use a different scheme for your input. For this scheme, you're using different analog voltage to represent different numbers. But if you have a nonlinear IV curve, then that means at a different voltage, that same cell represent a different number. So in that case, you have to fix your input voltage amplitude. To represent still different numbers, you use a fixed voltage pulse, fixed amplitude, but you can use a different number, right, of the pulses, or different duration of the pulses to represent different number. That, for example, is one way to deal with the so-called nonlinearity. But if you have the nonlinearity of drift, so over time, your resistance changes. That is a much harder problem to deal with. So that's why when we engineer our device, we engineer in a way it can give you really stable conductance levels. So we actually sacrifice something else, such as the energy to program them. If you wanted to get a more stable device, and usually means you need to spend more energy to program them. And for inference application, fortunately, that is tolerable because you do not need to reprogram it often, given you have very stable conductance levels. As you see in my experimental demo, we program the device, program the array, and we let it sit there for 6 months, and we remeasure it, to perform the same task. It didn't change. The result didn't change. That means the drift is really minimal. But that's not true for every type of RM, and it is not true for every other type of non-volatile memory. So there are non-volatile memory, it is called non-volatile, such as flash. Only if you say it's a binary, or it is, if you use it as 8-bit 256 levels, you probably cannot call it non-volatile anymore, because it will still have a little drift over time. If you use it as 256 levels, the room between two levels become much smaller. The little drift within a couple of days will already give you errors. So for those, you will have to refresh it from time to time. And so that is probably doable on some edge applications, but of course you will know the overhead. You have to have somewhere to store the real weight, right? And you need to read it and rewrite it there. You also need to have all the algorithm circuitry overhead. And sometimes if you use it in space, you probably do not even have the capability to refresh it. So those are our trade-offs, and we need to consider.
Thank you, Joshua. I mean, it's a really great presentation, and thank you once again. Professor Joshua is presenting this talk from Bulgaria, so thank you so much for being, very late over there and then giving us this presentation. So I will quickly go through the next week's presentation. Our speaker had an emergency and he's traveling and he canceled. We are looking for a speaker for next week. If we cannot find a speaker, then we will see on June 20th. Puneet Gupta from UCLA will be giving that talk. Thank you all.
Thank you.